What I am about to share with you will likely sound like pure blasphemy, especially coming from someone who has devoted their life to physics. It stands in direct opposition to the core narratives we are taught regarding the triumph and authority of science. It is a notion that, to be perfectly candid, disturbs my peace even after half a century of working in this field. The truth is, physics is incapable of furnishing a complete portrait of reality, not in any absolute sense, not in the manner we truly desire, a picture that reveals what is genuinely out there, existing on its own terms, independent of our act of observing it. I am not referring to mere practical constraints, a shortage of data, inadequate computational resources, or equations that are too difficult to solve. I am pointing to something far more profound, something woven into the very fabric of our scientific methodology. It is an issue rooted in measurement, in observation, and in that enigmatic frontier separating the quantum realm from the classical world we inhabit. My name is Leonard Susskind, and my professional life has been dedicated to exploring quantum mechanics, black holes, and the foundational principles of physics. And the deeper my understanding has grown, the more I have been forced to acknowledge that physics, at least in its present form, provides us with an instrument for making predictions, not necessarily with a description of what is fundamentally real. Allow me to begin with quantum mechanics, for it is here that this dilemma becomes impossible to ignore. Quantum mechanics represents the single most triumphant scientific theory ever conceived. It captures the behavior of atoms, molecules, light, and fundamental particles with breathtaking accuracy. Every modern device you utilize, computers, smartphones, lasers, medical scanners, depends upon its principles. Its performance is nothing short of spectacular. Yet, quantum mechanics harbors a deeply troubling secret, a quandary that has shadowed the theory since its formulation in the 1920s, a puzzle that has fueled a century of debate among physicists, a problem for which there is still no consensus solution. This is known as the measurement problem. Let me outline it. In quantum mechanics, the condition of a system, be it an electron, a photon, or an atom, is described by a mathematical entity called the wave function. This wave function encodes all conceivable information about that system. According to the Schrödinger equation, the foundational law of quantum mechanics, the wave function evolves in a flawlessly deterministic and predictable manner. Given the wave function at one moment, you can compute it for any future moment. There is no randomness, no uncertainty, only smooth, deterministic progression. But then you perform a measurement, and something utterly bizarre occurs. When you measure a quantum system, when you determine if an electron's spin is up or down, when you ascertain which slit a photon passed through, when you detect an atom's position, the wave function ceases to evolve according to the Schrödinger equation. Instead, it collapses, instantly, discontinuously, randomly. Prior to the measurement, the electron existed in a superposition, a quantum blend of both spin-up and spin-down. After the measurement, it is definitively one or the other. The wave function has collapsed from a spread-out superposition into a single, definite state. And here lies the crux of the problem. This collapse is not described by the Schrödinger equation. It is an entirely separate postulate, an additional rule grafted onto the theory that does not logically follow from its fundamental dynamics. Consequently, we are left with two utterly distinct modes of evolution in quantum mechanics. First, unitary evolution, smooth, deterministic, reversible, governed by the Schrödinger equation. Second, measurement evolution, discontinuous, probabilistic, irreversible, governed by we simply do not know what. This is the essence of the measurement problem. Why do we require two separate sets of rules? What exactly qualifies as a measurement? Where does one rule end and the other begin? What is so special about the act of measurement? And most disquieting of all, what is the true state of reality before we choose to measure it? Now, numerous interpretations of quantum mechanics have been proposed to resolve this dilemma. I wish to discuss them, for they illuminate something profound about the boundaries of physics. The most renowned is the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s. In essence, the Copenhagen interpretation advises us not to inquire about what is real prior to measurement. Physics, it asserts, is concerned with predictions, not with depicting an underlying reality that exists independently of observation. According to the Copenhagen view, the wave function is not a depiction of reality. It is a computational tool for calculating probabilities. It informs you of what you will observe when you conduct a measurement, but it remains silent on what is genuinely present before that measurement takes place. Within this framework, measurement is special. It is the interface where the quantum world connects with the classical world. It is the moment where mere possibilities solidify into actualities. But you are instructed not to ask how it works. Do not question what physical mechanism triggers the collapse. That, we are told, is not a question physics is equipped to answer. Bohr himself was quite explicit on this matter. He stated that the goal of physics is not to uncover what nature is, but to discover what we can say about nature. Physics describes our knowledge, our observations, our measurements, not reality in and of itself. This stance troubled many physicists, Albert Einstein most famously. Einstein is often quoted as saying, "I like to think the moon is there even when I am not looking at it." He believed in an objective reality that exists irrespective of observation. The Copenhagen interpretation appears to deny this, or, at the very least, it refuses to make any claims about it. From a Copenhagen perspective, asking whether the moon exists when unobserved is not a meaningful scientific inquiry. Yet here is what is truly remarkable. The Copenhagen interpretation works. It yields impeccably accurate predictions. It correctly forecasts the outcome of every experiment ever conducted. It has been tested relentlessly for 100 years without failure. Therefore, if physics is solely about generating predictions, if all we seek is a tool that tells us what our instruments will display, then the Copenhagen interpretation is perfectly sufficient. Physics can describe what we will observe. What it cannot describe, what it explicitly declines to describe, is a reality independent of that observation. Naturally, not everyone finds Copenhagen satisfactory. Alternative interpretations have emerged in an attempt to furnish a more realistic picture. The most prominent alternative is the many worlds interpretation, proposed by Hugh Everett in 1957. In the many worlds view, there is no such thing as wave function collapse. The wave function always evolves smoothly and continuously, obeying the Schrödinger equation without exception. When a measurement is performed, the universe undergoes a branching process, splitting into multiple parallel branches, one for every possible outcome of that measurement. In one branch, you record a spin-up result. In another, you record spin-down. Both outcomes are equally real and occur. You simply cannot perceive the other branches. In a certain sense, this resolves the measurement problem. There is only one rule: unitary evolution. No collapse. The Schrödinger equation governs everything. However, the price for this resolution is steep. You must accept the existence of an infinite multitude of parallel universes, ceaselessly branching every single time a quantum event occurs anywhere. Furthermore, these other branches are forever beyond your ability to observe or access. Does this constitute a description of reality? Perhaps. But it is an extraordinarily strange description, one that posits a vast, hidden architecture of existence that is, in principle, utterly unobservable. Another interpretation is pilot wave theory, also known as the de Broglie-Bohm theory. Within this framework, particles always possess definite positions, even when we are not measuring them. Their motion is guided by a quantum potential derived from the wave function. A measurement merely reveals the positions that were already definitively there. This offers a more classical-seeming picture. Particles follow specific trajectories. They are always in a definite location. Reality is fully specified at every instant. Yet these trajectories are profoundly non-local. The position of one particle can be influenced instantaneously by the state of other particles arbitrarily far away. Moreover, the guiding wave function itself can never be directly observed. It is a hidden structure that orchestrates the particle's motion. So once again, you obtain a description of reality, but it incorporates elements that are fundamentally inaccessible to observation. There are numerous other interpretations as well. Objective collapse theories, where the wave function collapses spontaneously when a system reaches a certain size or complexity. Quantum Bayesianism, where the wave function represents an observer's subjective state of knowledge. Relational quantum mechanics, where properties only exist in relation to other systems. Each interpretation paints a radically different portrait of what is real in the quantum realm. Each one makes identical predictions for what you will observe, yet they disagree profoundly on what is actually transpiring when you are not looking. And here is the pivotal issue. We possess no definitive method to choose between them. They all function. They are all mathematically consistent. They all generate the same experimental predictions, yet they tell completely different stories about the nature of reality. So what exactly is physics describing? Is it describing a multiplicity of worlds, guided particles on hidden trajectories, or is it merely describing a catalog of measurement outcomes? The honest answer is that we do not know, and there exists no conceivable experiment to decide the matter, because all interpretations are engineered to yield identical predictions. Physics can inform us of what we will observe, but it cannot tell us what is real. Now, let me address another dimension of this problem that I find deeply concerning: the quantum classical boundary. In quantum mechanics, small systems, atoms, photons, electrons, behave in quantum ways. They exist in superpositions, they exhibit interference, they display wave-particle duality, all the peculiar quantum phenomena. Conversely, large systems, cats, chairs, laboratory instruments, behave classically. They possess definite properties. They are in one distinct state or another, not in superpositions. They do not obviously interfere or tunnel or manifest quantum behavior. Where, then, is the boundary? At what precise point does a system cease being quantum and start being classical? The Copenhagen interpretation locates this boundary at the moment of measurement. The measuring apparatus is classical. The entity being measured is quantum. Measurement itself is the interface. But what qualifies as a measuring apparatus? Must it be a sophisticated scientific instrument? Does a simple interaction with the surrounding environment count? Does it necessitate a conscious observer, or is any macroscopic object sufficient? The theory does not provide clear answers. It is inherently ambiguous, and this ambiguity is not a minor technical oversight. It represents a fundamental gap in our comprehension. The phenomenon of decoherence, elucidated in the 1970s and 80s, offers some clarification. Decoherence is the process whereby a quantum system loses its distinctive quantum characteristics through interactions with its environment. A quantum system in a superposition, when it interacts with a vast number of particles in its surroundings, effectively begins to behave classically. The superposition technically still exists within the mathematics, but it becomes spread out across so many environmental degrees of freedom that it becomes impossible to detect in practice. Decoherence explains why macroscopic objects appear classical to us. They are perpetually interacting with air molecules, photons, and thermal vibrations, and these interactions destroy quantum coherence with incredible rapidity. However, decoherence does not solve the measurement problem. It explains why we do not perceive macroscopic superpositions, but it does not explain wave function collapse. From a purely mathematical standpoint, the wave function, even after decoherence, remains in a superposition. It is just that the different branches have decohered and can no longer interfere with one another. Thus, we still lack a clear answer to the questions of when, how, or even if wave function collapse genuinely occurs. We only know that we, as observers, record definite outcomes, and the theory does not elucidate why. This leads me to an even more fundamental concept: complementarity. Bohr's principle of complementarity states that quantum entities possess complementary properties, properties that cannot be measured simultaneously, properties that are mutually exclusive: position and momentum, wave nature and particle nature, Witch path, information, and interference patterns. You can measure one property or the other, but never both at the same time. Furthermore, the design of your experiment, your choice of what to measure, determines which property you will actually observe. Consider the classic double-slit experiment. You can observe wave-like behavior, an interference pattern, if you refrain from measuring which slit the particle passes through. Conversely, You can observe particle-like behavior, definite paths, if you do measure the particle's path at the slits, but you can never observe both manifestations at once. This implies that the properties you perceive are contingent upon how you choose to look. The experimental arrangement itself determines which aspects become real, in a sense. This raises a profound philosophical question. Are these properties intrinsic to the system itself, or are they created by the very act of measurement? According to the Copenhagen interpretation, properties only come into existence within the context of a specific measurement. A photon does not have a definite position until you measure its position. It does not possess a definitive wave-like or particle-like character until you arrange an experiment designed to reveal one aspect or the other. Reality, in this view, is contextual, observer-dependent, and measurement-dependent. This stands in stark contrast to classical physics. In a classical worldview, objects possess properties independent of observation. The moon has a specific position and velocity whether anyone looks at it or not. A baseball follows a definite trajectory, whether it is tracked or not. But in the quantum realm, properties seem to depend on the act of observation, with different observational methods revealing different complementary facets of the system. So, what is the system truly like, independent of any observation? Complementarity suggests this question may be unanswerable, or that the answer itself depends on how you choose to frame the inquiry. Physics can describe what you will observe given a specific measurement, but it cannot describe what exists independently of all potential measurements. At this point, you might reasonably object, "Lenny, this all sounds very philosophical, but does it really matter?" Physics makes accurate predictions, and those predictions work brilliantly. Who cares if we can describe an underlying reality, so long as we can forecast our observations? That is a perfectly fair point. From a practical instrumentalist standpoint, physics is an unqualified success. We can predict phenomena, engineer technologies, and build incredible machines without needing a complete picture of what is really happening. Yet, I believe it does matter. Not just philosophically, but scientifically. If physics is inherently incapable of describing reality, if the best we can achieve is a description of our own observations, then we are perpetually one step removed from the world as it exists in itself. We are merely describing our interactions with the world, not the world independent of us. This imposes a limitation on our understanding. It restricts the kinds of questions we are permitted to ask. It defines the boundaries of possible knowledge. Consider these questions. What transpired in the earliest moments of the universe, before any observers could possibly have existed? What is occurring right now in a distant galaxy where no measurement is taking place? What unfolds inside the event horizon of a black hole from which no information can ever escape to be measured? If physics is strictly limited to describing measurements, then these questions lie outside its legitimate scope. We cannot make meaningful statements about what is real in contexts where measurement is impossible. This troubles me deeply because I yearn to understand what the universe is like, not merely what my instruments report when I interact with it. Let me provide another concrete example. The black hole information paradox. This is an area I have worked on extensively, and it perfectly illustrates the problem. When matter falls into a black hole, what becomes of the information it carries? According to quantum mechanics, information cannot be destroyed. This is the principle of unitarity, a cornerstone of the theory. Yet, according to general relativity, anything that crosses the event horizon is lost forever, destined for the singularity. Stephen Hawking argued that black holes evaporate over time, emitting thermal radiation, and such radiation carries no information. This suggested that information is ultimately destroyed, violating quantum mechanics. This contradiction sparked a monumental controversy. If information is destroyed, quantum mechanics is violated. If it is not destroyed, general relativity seems to be violated. Something fundamental had to give way. After decades of intense research, the prevailing modern view is that the information is not lost. It is thought to be encoded in extraordinarily subtle correlations within the Hawking radiation. However, the precise details of how this works hinge on a theory of quantum gravity, which we do not yet fully possess. The relevance here is this. The question of whether information is lost is fundamentally a question about what is real inside the black hole. Is the information genuinely preserved in some form, or is it irretrievably destroyed? An instrumentalist, Copenhagen-style approach would dismiss the question as meaningless, since we can never measure the interior of a black hole directly. We can only measure what emerges from it. But that dismissal is profoundly unsatisfying. We want to know what happens to the information. We desire a description of reality that applies even in regions where direct measurement is impossible. Pursuing that goal requires moving beyond the Copenhagen interpretation. It necessitates a belief that physics describes something objective and real, something that exists independently of being measured. Yet we do not possess a version of quantum mechanics that accomplishes this cleanly and uncontroversially. Every serious attempt, many worlds, pilot wave, objective collapse, introduces elements that are unobservable or philosophical assumptions that many find difficult to accept. So we find ourselves at an impasse. We can make predictions, we can perform calculations, we can engineer marvels, but we cannot construct a description of reality that is fully coherent and satisfying. When I was younger, I was convinced the measurement problem would eventually be solved. I believed we would uncover a deeper theory, perhaps quantum gravity or string theory, that would definitively explain wave function collapse, clarify the transition from quantum to classical, and gift us a clear, unambiguous picture of what is real. However, the more I have studied and learned, the more I suspect the problem might be more fundamental than a mere gap in our current theories. It may not be a defect that will be remedied by a future, better theory. It might instead represent a permanent limitation on the very enterprise of physics. Physics provides us with a mathematical framework for predicting observations. This framework is staggeringly successful. Yet the framework does not uniquely determine an ontology, a definitive picture of what exists. Different interpretations attach radically different ontologies to the same, unchanging mathematics, and perhaps that is simply the way it must be. Perhaps physics is inherently incapable of telling us what is real. Perhaps it can only tell us what we will observe. Perhaps the map is not the territory, and the map is the only thing we can ever hope to possess. I find this notion deeply unsettling, but it may very well be the truth. Let me conclude with this reflection. Physics stands as the most successful intellectual endeavor in human history. It has granted us understanding, predictive power, and control over the natural world that would have appeared miraculous to our ancestors. But physics has its limits. It cannot tell us why the fundamental laws are as they are. It cannot explain why there is something rather than nothing. And if my concerns are valid, if the measurement problem reveals a truly fundamental constraint, then physics cannot fully describe a reality that exists independent of observation. This does not diminish the immense value of physics. It simply calls for humility regarding what it can and cannot accomplish. So the next time you hear someone proclaim that physics holds all the answers, or that we are on the verge of a theory of everything that will explain the complete nature of reality, remember this: we still lack a universally accepted explanation for what happens when you measure the spin of a single electron. Physics, in its present state, cannot describe reality. Not completely, not yet, and perhaps not ever. Acknowledging that limitation is the essential first step, whether our ultimate destiny is to one day transcend it or to finally and humbly accept it. Thank you for listening. Physics is a powerful tool, but it is not an omnipotent one.